Welcome students to this session number 22 on industrial metallurgy. These are the contents that we'll cover in this session. Well, in the last two sessions, I discussed with you that what is the meaning and the conclusions to be drawn when we say we are doing equilibrium cooling of a type 1 alloy. Example taken was of a copper nickel alloy of 65% nickel and remaining copper composition. You see, when we say equilibrium cooling means very slow cooling. But in industry, productivity is a big concern. So in industrial conditions, the rates of cooling that are followed are very rapid as compared to what are the requirements of equilibrium cooling. So generally, we would be following non-equilibrium cooling conditions for a metal or an alloy system. So let us now see that if rather than doing equilibrium cooling, we start doing non-equilibrium cooling for an alloy, what would happen? You see, you start from this temperature, you come to this temperature, solidification starts. And when solidification starts, who gives you the chemical composition of the first solid phase that is seen? We draw the tie line, and this end of the tie line gives us the chemical composition of the solid phase, that is S0 point. Then as the temperature drops from TB to TC, the chemical composition of the liquid phase is given by L1 and chemical composition of the solid phase is given by S1. Please try to appreciate that when we are doing equilibrium cooling, for this drop in temperature, from temperature liquidus temperature or temperature say TB to TC, the chemical composition of the solid phase has changed from S0 to S1. So this is the total shift. This is the total shift that has taken in the chemical composition of the solid phase, S0 to S1, when the temperature drops from TB to TC. And who brings about a change in the chemical composition of the solid phase? In the last session we discussed, it's the diffusion process. But what does diffusion need? Diffusion needs time. And when you are doing equilibrium cooling, there is ample of time and there is sufficient of time for the diffusion process to get completed. So when the diffusion process gets completed, means when you are doing equilibrium cooling, for this drop in temperature, the shift in the chemical composition of the solid phase due to diffusion is this. But students, if now you are doing non-equilibrium cooling, you will reach from temperature TB to TC, but diffusion would not get the same amount of time as it used to get during equilibrium cooling. So diffusion would not be able to make the shift as it could make during equilibrium cooling. So now if it made a shift from say here, say 95% to say somewhere around 90%, if it made a 8% shift in the chemical composition, depending upon the non-equilibrium cooling, the shift would be always less than 8%. So shift would somewhere be between S0 and S1. It cannot be a shift. The chemical composition change because of diffusion cannot be under non-equilibrium conditions, can never be as large as S0 to S1. So for the non-equilibrium cooling that we might have followed, I am assuming that we could not shift the chemical composition of the solid phase till S1, but rather we made a shift from S0, but we came till S1N. S1N means under non-equilibrium conditions S1. Similarly, students, when the temperature drops from point C to point D, for that shift in temperature, drop in temperature, diffusion process changes the chemical composition of the solid phase under equilibrium conditions by an amount S1 to S2. But if these are non-equilibrium cooling conditions, then the shift in the solid phase will not be this much, but we'd be somewhere in between this. So the shift is from S1 till S2N, right? Because I'm at temperature TD, so I have to show the shift over here. Then when the temperature drops from TD to TE, shift ideally should have been from S2 to till point E. But because we are doing non-equilibrium cooling, the shift would be somewhere from between S2 to E, and I have taken it as En. Now, please appreciate that had you been doing equilibrium cooling, when you go from temperature TB down till temperature TE, this temperature TB is TL, equilibrium liquidus temperature, TE is representing the equilibrium solidus temperature. Solidification would have been complete. Why did you assume that solidification would have been complete at point A? Because if you draw a tie line at point E, the chemical composition of the solid phase is given by this point, which is the same as is the chemical composition of the alloy taken. So when the chemical composition of the solid phase becomes equal to the chemical composition of the original alloy that had been taken, that's an indication that solidification is complete. But now when you are doing non-equilibrium cooling, what is the chemical composition of your solid phase? It's being given by point En, and since point En is not the alloy composition, see we are here, we had to be here, so that means that still further cooling is required for solidification to be complete. So now this line that this line that gets generated by joining all these non-equilibrium solid composition points, this is again a solidus line, but this is not equilibrium solidus, this is called non-equilibrium solidus. And because this is below the equilibrium solidus line, this line is called non-equilibrium solidus or depressed solidus. It is also sometimes referred to as the effective solidus, means the actual solidus under non-equilibrium cooling. And if you now extrapolate this line, you will see that this line cuts the alloy composition point somewhere over here. So here the solid phases composition becomes equal to the alloy composition. So it is this temperature at which the solidification practically gets completed. It should have rather got completed over here. So that explains the non-equilibrium cooling of a solid solution alloy under rapid cooling conditions. So let's see now what are the same things. I've discussed each of these things over here. The newer thing is that this temperature at which practically the solidification takes place under non-equilibrium conditions is called the effective solidus temperature, or the depressed solidus temperature, or the non-equilibrium solidus temperature. If this line was, whatsoever names are given to this line, non-equilibrium solidus, depressed solidus, effective solidus, the same names are given to this temperature: non-equilibrium solidus temperature, or depressed solidus temperature, or the effective solidus temperature. So students, what are the consequences then of non-equilibrium cooling? What are the conclusions? See, the first conclusion is that the solidification range has increased. Whereas under equilibrium conditions, the solidification temperature range is TL to TS, but now solidification completes at a still lower temperature. So solidification range has increased. Point number 2, which we have discussed, that under equilibrium conditions, the chemical composition of the solid phase is governed by the equilibrium solidus line, but under now non-equilibrium conditions, the chemical composition of the solid phase is governed by a depressed newer line, which is called effective solidus, non-equilibrium solidus, or depressed solidus line. And so these two conclusions or consequences were what you can see from the diagram. What you cannot see from the diagram is the third conclusion, and as I discussed in case of equilibrium cooling also with you, that when the solidification is proceeding, when the chemical composition of the solid phase is changing, it is changing because of the process of diffusion. And during equilibrium cooling, otherwise students, what is happening even under equilibrium cooling or non-equilibrium cooling also, if you look at the first solid that gets formed, very rich in higher melting point constituent, very rich in higher melting point constituent. So this all is solid, but we do not want solid of this. We need solid which is of 65 nickel. But initially the solid that is getting formed is of about 95 nickel, again 90 nickel. Do you get my point? But in the end, see, the last solid that will get formed, this is the last liquid that would convert into a solid. This is again not of 65 nickel. This is very rich in the other element, that is copper, the low melting point. So the initial solid that was getting formed is rich in the higher melting point constituent, that is nickel, and the later solid that is getting formed is rich in the lower melting point constituent, that is copper. So this solid that you actually require, you require it to be everywhere of 65 nickel, 35 copper. Now, during equilibrium cooling, as I discussed with you, because diffusion is getting all that time which it needs to get completed, in the end, the solid that you get, see, initially during equilibrium cooling also, this is the critical nuclei, then it grew into a dendrite, then further cooling it grew into a bigger dendrite, then with further cooling it grew into a bigger dendrite, and as it keeps on growing, initially whatsoever critical nuclei and dendrites were there, initially they were of higher melting point nickel, and the later part of the dendrite that is getting formed is of lower melting point constituent. And if diffusion is not able to complete, this solid will get formed like this. And in that solid, you will see that in the middle portion of the grains, the core of the grains are rich in the higher melting point constituent element of the alloy. And the regions close to the grain boundaries or the outer fringes of the dendrites are rich in the lower melting point constituent of the alloy. So in case of copper nickel, copper is the lower melting point. The excess of copper would be close to the grain boundaries or in the outer fringes of the dendrites. Nickel is the higher melting point constituent. The middle portion of the dendrite or the grain would be rich in nickel. But so if equilibrium cooling is done, diffusion will eliminate all these dendritic zones. But if non-equilibrium cooling is there, fast cooling is there, and diffusion process is not able to keep pace with the crystal growth, the crystal growth is taking place very rapidly, because crystal growth, dendritic growth, grain growth depends upon cooling rate that you are following. The faster you cool, the more rapidly the grain growth will, the dendrite growth will, the crystal growth will take place. But because of this rapid cooling, diffusion is missing its very important parameter, that is time. Because of that fast cooling, because time is not available, diffusion gets incomplete. So diffusion process, rate of diffusion lags behind rate of crystal growth, and that type of a solid will be cored. Why cored? There would be a core area, a middle area, which contains one type of an element, one type of a constituent, and there would be an interpharyngeal area near to the grain boundaries, which would be containing more of the lower melting point constituent. This type of structure is said to be suffering from a problem called coring or dendritic segregation or enveloping or surrounding, and it will deteriorate all mechanical properties of your material system. So we need to get rid of it, which we'll discuss in the sessions to come. I hope you understood these things and enjoyed the session. Thank you so much for being there.